Okay, in this class, a single phase full wave AC voltage controller has a resistive load of R is 10 ohm and the input voltage Vs is 120 volt RMS and 60 Hz. The delay angle of the thyristor T1 and T2 are equal pi by 2. Determine the RMS output voltage. We have calculated already this. The input power factor we have calculated. We need to calculate the average current of the thyristor IA, the RMS current of the thyristor IR. Here you can see, so here one thyristor conducts for first half cycle, another thyristor conducts for next half cycle. We need to calculate the RMS, we need to calculate the average current of the thyristor IA. So if you plot only this currents, average current of the thyristor IA, it looks like I can show you here. Average current flowing in the is only this much. Because thyristor T1 conducts in positive half cycle, the waveforms of the thyristor T1 current is this. This is sinusoidal from alpha to pi, and 0 to pi it is 0, and pi to 2 pi it is 0, and same waveform repeats in the next cycle. So we need to take the average for these waveforms. We need to calculate the average for these waveforms. So this continues still here. From here to here, we need to consider as a period of these waveforms. So from here to here, okay, this total distance is 2 pi, correct? 2 pi. We need to take average for this. Okay. If you take average for this, you can see here, I can call this as I, average or a DC value or average or DC of thyristor T1, thyristor T1. This is equal to integration from alpha to pi, so divided by 2 pi. The waveforms looks like Vm sin omega t d omega t. So this is a simple integration from alpha to pi Vm sin omega t d omega t. So you can ask a question, so why you are not taken any part from pi to 2 pi? Means the pi to 2 pi amplitude is 0, that's the reason it is 0. Only we need to take from alpha to pi. This is a current which is flowing through T1. So you can see in the simulation also whether it is correct or not. See, he is asking us right now, what is the current flowing through this transistor, through this SCR1? I will remove all these currents. See, this is a current which is flowing in through SCR1. So alpha to pi it goes, and pi to 2 pi it is 0. So we should integrate from here to here its value. Okay. So we'll do these calculations. So this is equal to 1 by 2 pi. Vm I will keep outside, it is a constant. Sin omega t, this is integration minus cos omega t. Limit alpha to pi. So this becomes Vm by 2 pi. Can is capital letter Vm? Okay, 2 pi. So minus cos pi is minus, so minus of minus 1, then minus of minus plus cos alpha. So here minus is there, so that's the reason this becomes Vm divided by 2 pi 1 plus cos alpha. You substitute values here. Vm by 2 pi. Okay, there is one mistakes we did here. Can you check? So here it's a current, that's the reason everywhere I should write Vm by R. So if I write Vm by R here inside, this also becomes Vm by R. So here also I should write R outside R. So here also R into 2 pi into 1 plus cos alpha. In denominator 2 pi R is there. R is there, 2 is there, pi is there. Okay, you can substitute this. So what is Vm? Vm is how much? So given voltage is 120. So given source voltage is 120. That's the reason I should write this right now. Shall I write this value somewhere here? Okay, or I will write somewhere here, right here. So IA This is a notation I have used right now. I can use some other also. You can use anything. IAT1. So Vm is 120 into root 2. 120 into root 2. Or you can calculate and you can keep that. R is how much? R is 10 ohm. So 2 pi 1 plus cos 90. 90 is, what is the firing angle in this problem? Is 90. 90 is cos 90 is 1, 0. So this becomes, you can see here, you calculate using your calculator, I think you will get value nearer to 2.7 amps. So this is average value of T1, means average current which is flow through thyristor T1. This is very important to find out the heat dissipated in the thyristor T1 while it is conducting. Okay. Next, what is the next part of your problem? The RMS current of thyristor, he has denoted it as IR. Okay, we'll calculate. So IR. So we have seen that your thyristor T1 from 0, if you call this as pi, and if you call this as 2 pi, if you call this as alpha, it starts conducting from alpha onwards. It conducts till pi, and it not conducts in from pi to 2 pi. So if you consider this as an alpha, and if this is my Vm, if you are having problem, I can show you. This is a waveforms. So this is a waveforms, which is the waveform, current waveform. This is my current waveform. For this waveforms, I should now take the RMS value, because through thyristor T1 only this current flows, correct? Through thyristor T2 this current flows, I can show you in your simulation. We already seen that this is a current which is flowing through thyristor T1. So this current RMS I should take. So it is starting from alpha and it is going till pi, and the mathematical model I can use is Vm sin omega t. From here to here it is 0. Only thing is we need to take RMS for this. Here I can show you, here we have already calculated it. So how you did it means I can rewrite, you can for your practice. here root mean, because the thyristor T1 is conducting from alpha to pi, and the period of that waveforms we have seen how it looks like. It is, if you consider this is my waveforms 0 to pi, it starts at alpha, follows like sine, then this. What is this value? It is Vm by R, because this is a current waveforms, starts at alpha 0. So we should write 2 pi alpha to pi Vm by R sin omega t whole square. So this part I should take whole square, because it is root means square value, d omega t, correct, alpha to pi, because from pi to 2 pi my thyristor T1 is not conducting. So whatever I am calculating here, it is for 1 SCR, So this is, strictly speaking, the RMS current, you can call R or RMS currents, the RMS current of the thyristor T, he has called as T, strictly speaking it is T1. T1. So this I already written here to save your times. Alpha to pi sin squared omega t d omega t. Here on it's just maths. Vm squared I kept outside. 2 pi r squared sin squared omega t d omega t. 1 minus cos 2 omega t by 2. R squared 2 pi Vm squared r squared 2 into 2 4 pi omega t alpha 2 pi sin 2 omega t by 2 alpha 2 pi minus alpha sin 2 pi minus sin 2 alpha by 2 Vm squared by r squared by 4 pi minus alpha 0 sin 2 alpha pi minus alpha plus sin 2 alpha squared 4 2 pi. I have written like this 4 pi I have considered as a 2 into 2 pi. My intention is to keep this Vm outside, and this 2 I have kept outside, so it has become root 2 Vm by root 2 to R. The left is written here. So this Vm by R into Vm by root 2 is nothing but V source RMS by R. So this is my formula finally I got. So what is the final formula I am saying here is in the textbook is called as RMS of IR of T, or you can call it RMS of T if you are having a confuse, RMS of T1, IRMS of T1, or some textbooks he has written as IR of T1, both you can follow it. So what is the formula? V source is how much? 120. R is how much? 10 ohm divided by root 2. So I'm substituting in this part. I'm substituting here this formula I'm using. So divided by 1 by pi minus alpha, it is pi by 2, plus sine 2 alpha. So pi sine it is like this, sine 2 into pi by 2 divided by 2. what is remaining here is 120, 10, 10 cancel each other. 12 divided by root 2, 12 divided by root 2, 1 by pi, 1 by pi. This is pi minus pi by 2, pi by 2. And this is sine, 2 cancel with this sine, 2 sine pi is 0, 0. Then again this pi cancel each other. So this is 12 by, this is root 2, no? Yeah, it is in denominator. So 12, we'll say 12 by root 2 into root of 1 by 2. So I can write as 12 by 2, 6 amps. This is an RMS of the currents which is flowing through thyristor T1. Correct. We can see here, this is, if you plot this as an RMS, this is a current waveforms which is flowing through T1, thyristor T1. If I plot another waveforms here for thyristor T2, only difference here is, so it conducts somewhere here at pi plus alpha, pi this is pi plus alpha. It conducts here, means it conducts here from pi to pi plus alpha, but 0 to pi it not conducts. It starts conducting from pi plus alpha and it continues till 2 pi. This waveform and this waveform is same, but it is in different time durations. So average value, if you calculate, if the for thyristor T1, if you call this as IT1, and if you are calculating for IT2, you should get same value, means IT1 is equal to IT2, because you can see magnitude wise it is same. It is there from pi plus alpha to 2 pi. This is there from alpha to pi. Rest all same. That's the reason IT1 is equal to IT2, and you can commonly call it as IT or I average. Sorry, this is RMS. I RMS of T1 is equal to I RMS of T2. You can call as I RMS. What I am saying finally, I RMS of T1 is equal to I RMS of T2 is equal to I RMS of T, or here I can say that. Similarly, average value previously we have calculated for same waveforms. So average currents which is flowing through T1 is equal to average currents which is flowing through thyristor T2 is equal to average currents which is flowing through any of the thyristor T. So if you calculate average current for these two waveforms, either or for this or for this waveforms, it is giving you same, whether it may be RMS or average. In both cases, this waveform's value and this waveform's value is same. So the RMS currents which is flowing through thyristor T1 is 6 amps, and average currents which is flowing through thyristor we have previously calculated is something like 2.7 amps. We have shown here, see, 0 to pi we got this. So what is that? I can recall you. So I can call this as Vm by 120 root 2 pi into 10, this we already did already, plus cos pi by 2. So this value we got how much? It is something like 2.7 amps. Please read Rashid. He has solved this problem please go through it. Thank you.